This is FRQ 5-1. We have a block sliding down a ramp and colliding with another block. We have a small block of mass M released from rest at the top of a curved, frictionless ramp. The block slides down the ramp, moving with a speed 3.5 v0. When it collides with a larger block of mass 1.5 m at rest at the bottom, the larger block moves to the right at a speed 2 v0 immediately after the collision. Express your answers to the following questions in terms of the given quantities and fundamental constants. So we're not going to be given any numbers in this problem. We have h as the initial height of the first block. We have the masses of the blocks in terms of m, and we have the speeds of the blocks in terms of v0. So also included in this conversation is going to be acceleration due to gravity, little g. So that's, like I said, we're not going to get any numbers here. So part A says determine the height of the ramp from which the small block was released. So we're going to attack this from conservation of energy standpoint. I can't remember if I said this yet, but part A says how high is the ramp. So we don't even need to deal with the big block at this point. We can do an mgh equals 1/2 mv squared for the little block here at the top and here at the bottom. So I can say, let's just use capital M because that's the mass of that block, G, and then the height is actually H, so that's fine. So we have equals 1/2 M is the mass of that block. Now his speed at the bottom of the hill is 3.5 v0. So 3.5 v0, and we have to square that. So the masses cancel out, and so we get H is equal to, there's a few different ways you could do this, and you don't actually have to do the 1/2 times the 3.5 squared. What I did was I did v0 squared over 2 g, and then I put 3.5 squared over here. Again, simplifying the fraction, writing it different ways, it doesn't matter. Just be clear. And for me, this was the clear way to show that I was squaring the 3.5. You know, if you tried to do 3.5 squared in your calculator and divide by 2 on test day, it could be nerve-wracking and you could put a wrong answer down there and they might not give you credit for it. But right here, I made it obvious that I know I'm squaring the 3.5 and I know I have the 2 in the denominator. That's my thought process there. So how does the rubric go? 1 point for any use of conservation of energy, okay? 1 point for the correct UG at the top, so realizing that the gravitational potential energy was mgh at the top, and realizing this, that's 1 point there, 1 point here, and then 1 point for the correct answer. And this is the correct answer, v0 squared over 2g times 3.5 squared. So that's part A. Part B asks us to find the speed of the small block after the collision. So right out of conservation of energy and into conservation of momentum. And we know that momentum is conserved in this collision. It's all taking place on the flat surface, so gravity really doesn't play a part in it. We know the initial velocity of the small block is 3.5 v0. We know the initial velocity for the big block is 0. And the final velocity for the big block is 2 v0. So we just need to find the final velocity of the little block. So we've got the momentum, initial equals final. So the initial for the small block is m times 3.5, v0. Plus 0, because there's nothing for the big block, right? At the end, we have the mass of the small block, which is capital M. I'm just going to use x for final velocity of small block. Just to be clear, right? Plus the final velocity of the big block, which is 1.5 m times 2 v0, right? And a little bit of algebra gives you that x is 1/2 v0. So its velocity is cut in half. Keep in mind that it's possible that this block could have bounced backwards and you would have gotten a negative velocity for that. So be careful. How does the scoring go on this? 1 point for realizing conservation of momentum, 1 point for the correct initial momentum, 1 point for the correct final momentum, and then 1 point for the correct answer. So 4 points on part B. Part C says the large block slides a distance d before coming to rest. Determine the value of the coefficient of kinetic friction mu between the larger block and the surface on which it slides. So this is a great problem. It goes from conservation of energy to conservation of momentum. Now we're going to do the work energy theorem, right? That's the tact we need to take here. So the work done by friction causes a change in kinetic energy from whatever it was originally to 0. So the initial kinetic energy of this block after the collision is 1/2 mv squared. Now remember, the mass of that big block is 1.5 m. The speed of that big block after the collision is 2 v naught squared. So I get a 3 m v naught squared for the initial kinetic energy of the big block. The final is going to be 0. So the change in kinetic energy is going to be 3 mv naught squared. Now, what's going to change its kinetic energy? Well, work, right? The work done by friction. And so we know the formula for work is Fd cosine theta. Now we know it's doing negative work to slow it down. And since it's anti-parallel, we can just sort of dump that. Yes, it's a -1, but then you'd have to say that delta K is -3 mv naught squared. Either way, okay? The force of friction is mu K times the normal force. Since everything is level here, that's 1.5 m times g. Remember, the mass of the big block is 1.5 m. And then we've got our d because that's the distance. So what we end up here is the change in kinetic energy is equal to the force of friction, which is mu K times the normal force, times the distance. Technically, they should both be negative. The change in kinetic energy is negative, and the change in the work done is negative because the block's moving to the right, but friction is acting to the left. I'm going to get rid of all of that. And so I'm going to solve for mu K, and I get 2 v naught squared over GD. I should be clear here. This is a capital M. This is a capital M, so those cancel out. So there is my expression for mu in terms of all of the other variables. All right, let's talk rubric. 1 point. There were a couple of ways to go about this. The way I did it was 1 point for realizing that the work kinetic energy theorem or work energy theorem, 1 point for a correct expression for the work done, 1 point for the correct kinetic energy of the block, and then 1 point for the answer. They had another way of doing this with a kinematic formula where you could find a relationship between the force exerted by friction and turn that into an acceleration, and then solve that with kinematics. And oftentimes you can do that with work energy versus kinematics. If you did it with straight kinematics and didn't use work kinetic energy theorem, you could have a point for determining a relationship between acceleration and force, a point for a correct kinematic formula, 1 point for the initial speed of the block, and then 1 point for your answer. So if you did that and you're wondering if it's right, let me know. I think you probably would have gone work energy theorem on this one. Finally, part D asks whether the collision between the two blocks is elastic or inelastic and justify your answer. Now, I suppose you could have realized right off that it wasn't perfectly inelastic because they didn't stick together. But the question they're asking here is kinetic energy conserved or not? If it's conserved, then it's elastic, right? And if it's not conserved, then it's inelastic. And as far as I know, the only way to really figure this out is to just calculate it. So the initial kinetic energy, just the little block is moving, right? M, and it's moving at a speed 3.5 v naught squared. So I get 6.125 mv naught squared. That's the initial. Then final, we have block 1, which is 1/2 m, and it's moving at 0.5 v naught squared. Remember, we calculated that back here, right? That's the final speed of block 1. So for that, I get 0.125 mv naught squared. For block 2, 1/2 1.5 m. It's moving at 2 v naught. We square that, and we get 3 mv naught squared. So the total final is definitely less than the initial. So we say it's inelastic. Okay. So for the rubric there, 1 point for saying it's inelastic, 1 point for saying that the change in kinetic energy is not 0, or saying the kinetic energy is lost, or you could get 1 point for showing that they're lost. I'm not entirely sure how they give us 3 points for that. The rubric is a little bit wonky. It says 1 point for indicating the collision is elastic, so that's the right answer. 1 point for indicating that the reason it's inelastic is because the change in kinetic energy is not 0, or because kinetic energy is lost. And then another point for showing that it's not 0. Oh, I guess, okay, so the points kind of go in reverse order. 1 point for showing, doing the math, right? Then 1 point for saying, okay, well, these results mean kinetic energy was lost. And then 1 point for saying, because kinetic energy was lost, it's an inelastic collision. So 3 points for part D. And that's it.